Welcome viewers to the 20th and last lecture in the open online course Computer Numerical Control of Machine Tools and Processes. So, let us move right away to some discussion and multiple choice questions on the last 4 topics that we have covered. To start with, the first question, isoscallop machining is carried out by a ball-ended milling cutter machining a free form surface on a 3-axis CNC machine. Okay. So, isoscallop machining, ball-ended milling cutter, 3-axis machine, free form surface. In this case, scallop heights are same all over the surface. Second option, scallop height between 2 cutter paths is always same, but it is different from that between 2 other cutter paths on the same surface. Third, scallop height varies randomly, and D, none of the others. First of all, we can eliminate C. Yes, it is not correct. Scallop height has to be uniform. Second, A and B, they are A is suggesting, while A is suggesting that it is uniform over the whole surface, B is suggesting scallop height is uniform only for a particular cutter path. B is wrong. If isoscallop machining is being talked about, scallop height has to be the same all over the surface. So, option A is correct. In a 3-axis machining of a free form surface employing ball end milling cutter, the criterion of determining the forward step is, so we have not up till now mentioned whether it is isoscallop, isoplanar, isoparametric. So, it is the general case. So, the criterion is uniform surface roughness created by scallops, equal side steps orthogonal to cutter path, tolerable deviation from surface form, none of the others. Here, first of all, we are talking about forward steps, and uniform surface roughness created by scallops does not come into the picture. So, first one is not relevant. Second one also is talking about side steps and it is not relevant. So, A and B are gone. C reads tolerable deviation from surface form, and this is correct. We are tolerating a form tolerance of E from the designed surface, and that way C is the correct one. Sorry. If there are 18 control points, okay, 18 control points on a Bezier curve, the highest power of the parameter in the expression of the Bezier curve would be 19, 18, 17, 3, none of the others. Here we have already studied that if there is a Bezier curve with n number of control points, its highest power would be n minus 1. So, C is the correct answer. You make a MATLAB program for finding out the CL points. So, finding out the cutter location points. It might be one fixed point on the cutter, which may be the center of the ball end of the round nose tool. So, for finding out the CL points for cutting a free form surface with ball end milling cutter, ball diameter is also given 5 millimeters on 3-axis machining center. You upload a G and M code program with the CL points to the machine, but find that the cutter diameter is actually 10 millimeters. That means, there is an actual cutter mounted on the spindle or available with you, which you have to use, and that is having a diameter 10 millimeters, while your program has been made with the consideration of a ball diameter of 5 millimeters. So, as a consequence, the options are the form would not be accurate, no problem I mean, second option is no problem if you use this tool with this program, the surface finish is going to be better in fact. Third option, you declare 10 millimeter cutter diameter in offset file with G1, G41 and G42. That means you are taking the help of cutter radius compensation or cutter diameter compensation, and there you declare that the diameter is 10 millimeters and there will be no problem. And the fourth option is CC data should have been used, not CL data. So, let us investigate what could be correct. First of all, CC data should have been used, not CL data. This is not correct. We have had quite a good amount of discussion on this. CL data is required. So, D is gone. Next, the form would not be accurate. This seems to be correct, but first of all, let us find out about the others. No problem if you use this tool with this program, the surface finish is going to be better in fact. See, if you are finding out the cutter location for 5 millimeter diameter and using 10 millimeter diameter instead, naturally the surface which is going to be produced, it is going to be different. We are not bothered about the surface finish at this moment, we are bothered about the form, and the form will definitely be different, and therefore, B is not correct. Next is you declare 10 millimeters cutter diameter in offset file and use G1, G41 or G42 as the case may be. This is also not correct. Why? Because G41, G42 cutter diameter compensation or radius compensation is only applicable in planar machining, that means 2-dimensional machining, but here we are moving in 3 dimensions. So, cutter would not be able to make use of this and properly offset the tool in that case. So, C is also not correct, therefore, A is the correct answer. During CNC freeform machining by ball end milling on a 3-axis machine, the points on the freeform surface contacted by the cutter are the points through which the center of the cutter is moved, are the points through which the bottommost point of the cutter is moved, are called the cutter location points, none of the others. First one, are the points through which the center of the cutter is moved? Certainly not, because these are lying on the freeform surface, and therefore, if you move the center of the cutter through these, part of the workpiece will also be machined, which is definitely not what you want. Second option, are the points through which the bottommost point of the cutter is moved. This is also not correct, because the points on the freeform surface when contacted by the cutter should have the freeform surface and the cutter touching each other, tangential to each other. And if the bottommost point is just randomly put through these, it cannot produce the proper cutter path. Okay. Bottommost point might well not be tangential to these points on the freeform surface in all the cases. So, this is also not correct. These points are called the cutter location points. Not correct. Obviously, they are the cutter contact points. So, the answer is none of the others. A freeform surface is cut by a vertical plane. The normal to the surface at point x is not contained in the vertical plane. So, point x is, let me draw a figure. This is the surface and this is the vertical plane. And this point is point x. Okay. This is the point x. And we are saying that the freeform surface is having a normal at this point, which is not contained in the vertical plane. Okay. So, it is away from the vertical plane. In such a case, the intersection curve of plane and surface will not be contained in the plane. So, this means what we are saying is that this is the intersection curve, this will not be contained in the plane. This is the first option. This is absolutely wrong, because the intersection curve is definitely belonging fully to the plane and it is belonging fully to the surface. It is contained by both. Next option is the normal P. So, this is the normal P to the plane. This is normal P to the plane and this is N. Will not be orthogonal to N. This is correct. See, if it is perpendicular to P, if N is perpendicular to P, all lines which are perpendicular to P, they will lie on this particular surface. So, if it is away from this plane, it definitely cannot be orthogonal to N. So, second one is correct. Let us see the third one. The center point of the ball ended milling cutter having contact point at x. So, the center point of the ball ended milling cutter would lie on the plane. No, it will not lie, because it will lie on this particular line. So, maybe this is the cutter location. Okay. The center point of the ball ended milling cutter having cutter contact point at x would lie on the plane. No, it will not. It will lie on N, and N has been stated to be away from the vertical plane. Let us quickly go back once to this line. So, this we have investigated. The intersection curve of plane and surface will not be contained in the plane. This is absolutely wrong. The normal P to the plane will not be orthogonal to N. This is, we have found this out to be correct. And the center point of the ball ended milling cutter having cutter contact point at x would lie on the plane. Definitely not. It will lie on the normal, which is away from the plane, and none of the others. None of the others obviously is wrong. So, we have B, option B to be correct. In the isoplanar method of cutter path generation applied in case of free-form surface machining in 3-axis machining center with ball-ended milling cutter, the cutter contact points are the intersections of parallel vertical planes and the free-form surface. Okay, this we already know. In that case, it stated first, the CL points for one particular cutter path are always contained in the vertical plane. Not necessarily. They will be at the tips of the tangent, at the tips of the normal vectors at those very cutter contact points, and the cutter contact points are lying on a vertical plane, because they are found out by the intersection of vertical planes and the free-form surface. But these normals might well deviate from the vertical plane. So, this is not necessarily correct. A. The CC points for one particular cutter path are always contained in a vertical plane. This is correct, because they are formed by the intersection of a vertical plane and the free-form surface. Both the CC and CL points for one particular cutter path are always contained in the vertical plane. No, it follows from A that this cannot be correct, none of the others. So, the correct option is B. This I think we have already done. So, let us quickly move on. In a free form surface, the normal at any point is always parallel to at least one tangent at that point to the surface, is always vertical, can always be contained in a vertical plane, none of the others. So, first one, the normal at any point on a free form surface is always parallel to at least one tangent at that point to the surface. This is wrong, because the normal is always perpendicular to any tangent at that point to the surface. The normal at any point is always vertical. No, it can well be inclined, can always be contained in a vertical plane. This is correct. Any vector for that matter can be contained in a vertical plane. You just have to rotate a bit rotate a vertical plane a bit, and you will ultimately be able to contain that particular vector. So, the correct answer is C, can always be contained in a vertical plane. In a 3-axis machining of a free-form surface employing ball-ended milling cutter, cutter location data refers to location of the points of contact between cutter and the free-form surface. No, this is CC point. So, A is not correct. B, location of the control points on the surface. Control points have nothing to do with cutter location points. Location of the scallop points between the two adjacent positions of the cutter and the successive cutter paths. Scallop points have nothing to do with cutter location data. None of the others. So, answer is none of the others. Isoparametric machining is a popular strategy of cutter path generation as it is computationally non-intensive, none of the others. Cutter paths do not get clustered on one side of the surface and spread on the other. It produces uniform surface roughness. So, let us see, it produces uniform surface roughness, certainly not. That is the business of isoscallop machining. So, D is out. C, cutter paths do not get clustered on one side of the surface and spread out on the other. This is actually just the opposite is true for isoparametric machining. Cutter paths do get clustered on one side or may get clustered on one side, and they may spread out on another side. So, C is not correct. So, what remains is D and A. So, let us see A. It is computationally non-intensive. This is correct. Finding out cutter paths in case of isoparametric machining is extremely simple. So, correct answer is A. The normal to a Bezier surface at a point is normal to all tangents to the surface at that point. This is correct. Normal to only the u and v direction tangents at that point, wrong. Not normal to any of the tangents to the surface at that point, wrong. None of the others. So, the first option is correct, normal to all tangents to the surface at that point. Here I should mention that I will mainly restrict the questions on free form surface to conceptual questions and maybe questions based on simple calculations, but not generally numerical problems. Mainly questions of this type, and maybe say derivations, that small derivations that we have done, delta t is equal to root over etcetera for finding out forward steps. Those based on those I might be giving small derivational problems in MCQ form. In isoscallop machining of free form surface in CNC 3-axis machine with ball ended milling cutter, uniform surface roughness is obtained by uniform surface roughness across lay lines, that means perpendicular to the lines of cut. So, uniform surface roughness is formed by forward steps with circular arc approximation, forward steps of equal parametric increments, equal forward steps, equal side steps, none of the others. In this case, forward steps with circular arc approximation, it is not relevant. Forward steps and side steps cannot be, they are not connected with each other. So, A is not correct, B is also with the same logic not correct, C is also not correct with the same logic. D says equal side steps. Does it mean that, I mean it suggests that D states that you will get uniform surface roughness if you give equal side steps. This is incorrect. We have gone through quite a lot of calculations to understand how side steps can be found out in order to give uniform scallop height. So, equal side steps will not necessarily give us uniform surface roughness. So, none of the others must be correct here. In case of isoparametric machining of free form, FF means free form surface PUW by ball end milling cutter on a 3-axis machining center. So, this is isoparametric machining. Cutter path is along lines along which U is equal to W. None of the others. Lines of iso curvature and lines of iso height, none of these are correct. So, none of the others. Why? Because in case of isoparametric machining, the cutter paths coincide with the isoparametric lines, not iso curvature, neither iso height. Isoparametric lines mean along which the one of the parametric values will be constant. We have had discussion on this in previous lectures. A flat ended milling cutter cannot machine free form surfaces on 3-axis machines as it suffers from stress concentration. Perhaps what is suggested is that the flat ended milling cutter has a sharp edge at the very end of it, so that there can be stress concentration due to that sudden that sharp edge. B is cannot machine concave curvature. That means, if you have concave curvature on the body, the flat ended milling cutter cannot handle that. C cannot machine convex curvature, none of the others. Here the correct answer is cannot machine concave curvature. Due to the very shape of it, the flat ended milling cutter cannot go beyond a particular distance. Let me draw a quick figure, so that I can share the idea with you. If you have a surface with a concave curvature, okay, and if you have this particular end milling cutter, with teeth like this, it cannot go beyond this particular position, and it leaves behind this material uncut. This material is not removed by this cutter, because it is a 3-axis machine. It can only move this way, it can move that way, and it can move in and out of the paper. So, it has no way of machining, removing this material. But what if it has convex curvature? Does it have any issues with that? No, because it can cut from this side, it can machine here, it can go down this way in this particular plane and machine all those places. It has no problem with accessing any such places in the convex part. Concave, it gets stuck here, it cannot go beyond. So, cannot machine concave curvature. Let us come back to this. Cannot machine concave curvature is correct. B is correct. What about A? Suffers from stress concentration. The answer to this is, if it suffers from stress concentration, then it would not have been applicable in other cases also. So, this cannot be the reason for which it cannot machine free form surfaces. Had it been stated that it cannot machine anywhere, okay, any machining application, it is not applicable because it suffers from stress concentration, then we could have considered it. But the problem is, in that case, that sort of flat ended milling cutter would not have existed. Okay. If it cannot be used universally, it would not have existed in the first place. So, correct answer is B. 3-axis CNC machines cannot cut all free form surfaces, because 3-axis machines, they cannot cut all free form surfaces, because the real world is 4-dimensional. Now, is the real world 4-dimensional? We will consider the real world to be 3 dimensional now. Okay. So, the first one is not correct. B, free form surfaces might have re-entrant sides. C, 5-axis machine manufacturers hold a patent on machining some kinds of free form surfaces, and 3-axis machines cannot produce uniform side step and uniform surface roughness as 5-axis machines do, and none of the others. Here 3-axis machines cannot produce uniform surface roughness, uniform side step and uniform surface roughness, etc., but still they can cut free form surfaces. Okay. So, we cannot say that it cannot cut a free form surface because it cannot produce uniform surface roughness. At the very beginning, the logic is wrong. So, this is not applicable. Okay. So, 3-axis machines can definitely cut surfaces, but it is not true that we cannot say that it cannot cut a surface because it is not producing uniform surface roughness. So, this idea is wrong. So, we are not accepting D. 5-axis machine manufacturers hold a patent on machining some kinds. Frankly speaking, I do not know of such patents, and I would not be ready to accept this particular statement. So, C is also considered to be wrong by us. Free form surfaces might have re-entrant sides. Let us have a quick look what we are talking about. If there is a body like this, we are saying this is a re-entrant side. It cannot be accessed by a tool which is coming from the top, and it can only move down, side, and this side also. This cannot get inside, but if you have a tool which can rotate, its axis can rotate and it can take up this configuration, then it can get inside like this. Okay. 3-axis machines cannot do this, and therefore, 3-axis machines cannot machine all types of surfaces, because surfaces might be having this sort of a configuration which is called re-entrant side. So, answer B is correct. In 3-axis machining of a free form surface employing ball ended milling cutter, isoplanar strategy of cutter path generation refers to generation of cutter paths by intersection of surface with parallel vertical planes. So, we are talking about isoplanar strategy, and generation of cutter paths by parallel, this seems to be correct. A. Let us see. Generation of cutter paths along isoparametric lines of the surface, wrong. Generation of cutter paths along maximum concave curvature of the surface at every point, no. None of the others. So, A is correct. Question A is correct. In 3-axis CNC machining of a free form surface employing ball ended milling cutter, isoscallop strategy is considered to be superior to isoparametric, as isoscallop strategy is computationally less intensive of the two. This is not correct. Isoscallop strategy is in fact computationally more intensive. The side steps in isoscallop strategy, by the way, computationally less intensive or more intensive means that you have to put more computational effort in case of more intensive case. Less intensive means you have to put less computational effort. So, the side steps in isoscallop strategy are equal, while it is not so for isoparametric. Mind you, side steps are not equal in isoscallop. Scallop height is equal, but not side steps. So, B is also wrong. The radius of curvature of the surface orthogonal to the cutter direction. So, the radius of curvature of the surface orthogonal to the cutter direction is equal at all cutter contact points for isoscallop. This is not correct. This cannot be correct because it depends on the surface. It cannot depend upon the isoscallop strategy. Radius of curvature of the surface orthogonal to the cutter direction depends on the surface and not on the method. So, none of the others, it is correct in this case. So, with this, let me see how many other questions we have. Okay, that's the end. So, we come to the end of the lecture series, and I will review the lectures once again, and if I feel that okay, one or two lectures or notes, if it can be shared, I mean one more lecture or some extra notes, if it can be shared with you, and if some corrigendum is required, that means if there are some errors or mistakes or typographical errors or some mistake in delivery, I will add a note of corrigendum which will explain all those errors to all the viewers. So, thank you very much for being with us, and I am sure that it will be a very good experience both for you and for us. Thank you.